Look up at the night sky, and you might catch a glimpse of Venus, shining like a brilliant, steady jewel just after sunset or before dawn. For centuries, it has captivated astronomers, poets, and dreamers, our so-called sister planet, similar in size to Earth, wrapped in thick, mysterious clouds. But behind that beautiful veil lies a world of extremes. Surface temperatures hot enough to melt lead, crushing pressures, and skies filled with sulfuric acid. It sounds like the last place anyone would want to live, doesn't it? Yet, what if I told you that the most Earth-like environment in our entire solar system isn't on Mars or on some distant moon, but floating high above the deadly surface of Venus, suspended within its clouds? Yes, you heard that right. Scientists and visionaries are now seriously exploring the possibility of building floating cities in the upper atmosphere of Venus, where the temperature and pressure are surprisingly similar to those here on Earth. Imagine vast, shimmering habitats drifting gracefully among the golden haze, filled with gardens, laboratories, and homes, all designed to harness the planet's unique environment for human survival. This isn't just science fiction. It's a real, scientifically grounded concept gaining momentum among researchers at NASA and beyond. We're talking about a future where humanity doesn't just visit other worlds. We make them our own, turning one of the most hostile places imaginable into a new frontier for civilization. This idea touches something deep within us, that relentless human drive to explore, to adapt, and to imagine futures beyond the horizons we know. It speaks to our curiosity, our courage, and our boundless creativity. In this video, we're going to embark on a journey together, one that will take us from the earliest dreams of space colonization to the cutting-edge technologies that could make life in the clouds of Venus a reality. We'll uncover why Venus, of all places, offers such an unexpected opportunity, how we might actually build and sustain these floating settlements, and what it would mean for us as a species to call another world home. So settle in, open your mind to the extraordinary, and let's explore one of the most thrilling possibilities ever conceived, life among the clouds of Venus. So why would we choose such a seemingly hostile world over a seemingly more familiar one like Mars? It all comes down to a few critical and often overlooked advantages that Venus holds. We often hear Mars called the most Earth-like planet, but that's only true if we're looking at its surface through a telescope. When we examine the raw data of what human bodies actually need to thrive, Venus starts to look surprisingly hospitable, just not where you'd initially expect. First, consider gravity. Venus is almost a twin to Earth in size and mass, which means its surface gravity is about 90% of what we experience here. That might sound like a small detail, but for long-term human health, it's absolutely monumental. On the Moon or Mars, with their much weaker gravity, astronauts face severe health risks. Their bones lose density, their muscles atrophy, and their cardiovascular systems weaken no matter how much they exercise. A settlement on Venus would allow us to live under a gravitational force nearly identical to home, preserving our bodies and allowing for a much more normal, healthy existence. We could raise children there without wondering if their bones would be too brittle to ever visit Earth. Then there's the matter of radiation protection. The surface of Mars is bombarded by solar and cosmic radiation because it has a very thin atmosphere and no global magnetic field to deflect these dangerous particles. Anyone living there would need heavily shielded habitats or to live underground for protection. Venus, however, comes with a built-in solution. Its incredibly thick atmosphere, primarily composed of carbon dioxide, provides a phenomenal natural shield against radiation. At an altitude of around 50 kilometers above the surface, the atmospheric pressure is almost the same as Earth's at sea level, and the radiation exposure is comparable to what we experience in Canada. This means our floating habitats wouldn't need complex, heavy shielding. The planet itself would do that job for us, Now, the surface of Venus is undoubtedly a hellscape. With temperatures soaring to 465 degrees Celsius, hot enough to melt lead, and a surface pressure 92 times greater than Earth's, it's the last place you'd want to build a house. But that's the genius of this concept. We don't have to. Instead of fighting the planet's most extreme conditions, we can use its own nature to our advantage. The key is to look up into that sweet spot in the cloud layer. The carbon dioxide atmosphere that makes the surface so deadly is actually the very thing that makes floating cities possible. Because breathable air, a mixture of nitrogen and oxygen, is lighter than the dense carbon dioxide below, a large enclosed habitat filled with our air would naturally float like a blimp at that perfect altitude. We wouldn't need to constantly burn fuel to stay aloft. The physics of the atmosphere would do the work, providing permanent, effortless buoyancy. It turns the planet's greatest challenge into its most valuable asset. This brings us to one of the most fascinating concepts in planetary science, the idea of a Goldilocks zone, not on a planet's surface, but suspended high within its atmosphere. On Venus, this zone exists in a surprisingly narrow band, a literal sweet spot in the sky between approximately 50 and 60 kilometers above the inferno below. At this altitude, something remarkable happens. The crushing pressure that defines the surface eases dramatically, dropping to around 1 atmosphere, effectively the same pressure we experience standing at sea level on Earth. You could step outside a pressurized habitat here, and aside from the need for oxygen and protection from the acidic clouds, you wouldn't feel the overwhelming squeeze or explosive decompression associated with space or the Venusian depths. The temperature in this layer is equally forgiving, ranging from a chilly 0 degrees Celsius to a warm 50 degrees Celsius. That's a spectrum that runs from a cold winter day to a hot desert afternoon, conditions that our technology is exceptionally well equipped to handle. We wouldn't need to invent radical new heating or cooling systems. Standard insulation and climate control used in buildings across Earth would be more than sufficient to maintain a comfortable, shirt-sleeve environment inside a habitat. It's a pocket of almost mundane normalcy tucked within an otherwise alien and terrifying world. Think of it as an oceanic layer on Earth. The deepest parts of the ocean are pitch black, subject to immense pressure, and home to bizarre life forms adapted to extremes. But closer to the surface, in the sunlit zone, conditions are warm, pressure is normal, and life is abundant and familiar. The Venusian cloud deck is our sunlit zone. It's the only place in the entire solar system, outside of Earth itself, where a human wouldn't immediately require a massively pressurized suit to survive the outside environment. The primary challenges shift from battling impossible physics to managing chemistry and material science, specifically dealing with the sulfuric acid clouds that define this region. But even that, as we'll see, is a solvable problem, more akin to managing corrosion in an industrial setting than contending with the fundamental hostility of space. This altitude band isn't just a convenient option. It's the only place where the concept of a sustained human presence on Venus moves from pure fantasy into the realm of plausible engineering. But this remarkable environment presents its own unique set of engineering puzzles, starting with the very air we would need to breathe. The Venusian atmosphere at this altitude is overwhelmingly composed of carbon dioxide, around 96.5%, with the remainder being mostly nitrogen and trace amounts of other gases like sulfur dioxide and argon. It's a toxic, unbreathable soup, yet it holds within it all the fundamental raw materials we would need to not only survive but to thrive. The most elegant aspect of this challenge is also its most counterintuitive solution. On Earth, we fill balloons with helium or hydrogen because they are lighter than our nitrogen-oxygen atmosphere, providing lift. On Venus, the roles are completely reversed. The local atmosphere is so much denser, thanks to all that heavy carbon dioxide, that our regular breathable air becomes the lifting gas. a large envelope filled with a nitrogen-oxygen mixture, the same air we breathe every day, would be significantly lighter than the surrounding carbon dioxide and would experience a powerful buoyant force. This means the primary structure of a cloud city, its very foundation, could be a giant balloon filled with the same air its inhabitants are breathing. The habitat and the lifting gas are one and the same, creating an incredibly efficient and elegant design where the thing keeping you afloat is also the thing keeping you alive. Of course, we can't just open a window and scoop this air in from outside. Creating and maintaining this life-sustaining bubble would require sophisticated atmospheric processing systems. The first and most critical technology would be a system to extract the necessary elements from the Venusian air itself. Imagine massive intakes on the outside of the habitat, drawing in the thick, yellow-hued atmosphere. This gas would be run through a series of filters and processors. The primary goal would be to separate the incredibly abundant carbon dioxide into its component parts, carbon and oxygen. This is a process we are already developing for use on Mars, using a technology called solid oxide electrolysis. By applying heat and an electrical current, we can split carbon dioxide into carbon monoxide and pure, breathable oxygen. The oxygen would be stored for life support, while the carbon could be harvested as a valuable resource for manufacturing or even as a building material. Nitrogen, which makes up the bulk of our Earth's atmosphere and is a crucial buffer gas in our own air mix, is also present in the Venusian clouds, comprising about 3.5% of the atmosphere. While this seems like a small amount, the sheer volume of atmosphere available makes it a viable resource. Specialized separation units could concentrate and isolate this nitrogen, which would then be blended with the produced oxygen to create that perfect, breathable lifting gas. This entire operation will be powered by the one resource Venus has in unbelievable abundance: sunlight. The upper cloud layers are bathed in intense solar radiation, far more than Earth receives, making giant solar arrays an obvious and highly effective power source for these energy-intensive processes. This creates a beautifully closed-loop system. The planet provides the raw materials, carbon dioxide and nitrogen. The sun provides the power to process them. And the fundamental physics of the dense atmosphere provides the lift. The technological challenge shifts from fighting an alien world to intelligently harnessing its inherent properties, turning its hostility into utility and building a new home suspended in the golden skies of our sister planet. So what would these incredible floating outposts actually look like, and how would they function as more than just survival pods? The architecture of a Venusian cloud colony would be unlike any city we've ever built on Earth, born from the necessity to be both a habitat and a vessel, a home and a buoyant craft. We are not talking about building on a foundation of rock and soil, but engineering for a foundation of air itself. The most likely design wouldn't be a single massive structure, but a fleet of interconnected, modular habitats. Imagine a series of enormous, shimmering orbs or elongated blimp-like envelopes, tethered together to form a resilient and flexible community drifting serenely through the golden haze. The core structural principle is buoyancy through breathable air. Each individual habitat module would essentially be a giant, rigid or semi-rigid aerostat. The outer shell would need to be an incredibly advanced multi-layered composite, engineered for one paramount purpose beyond strength: resistance to corrosion. The clouds at this altitude are not made of water vapor, but are a mist of sulfuric acid droplets. Any exposed material would be under constant assault. Scientists are already researching super acid-resistant coatings, perhaps based on specialized ceramics or polymers like Teflon, or even exploring the use of certain metals like titanium or nickel alloys that exhibit a high natural resistance to acid. This outer cladding would be the colony's first and most critical line of defense, a high-tech skin designed to shrug off the corrosive environment. Beneath this protective shell lies the heart of the habitat, the vast interior volume filled with our Earth like nitrogen-oxygen atmosphere. This isn't just the air we breathe, it's the very thing that provides lift, making the entire structure a giant balloon. To maintain its shape and integrity against internal pressure and external forces, the framework could utilize a geodesic design. Much like the iconic Epcot Center sphere or the Biosphere 2 project, a lattice of incredibly strong yet lightweight carbon fiber or composite struts would form a spherical or cylindrical cage. This structure is phenomenally efficient at distributing stress, allowing for large, open interior spaces without the need for obtrusive internal support columns, creating a feeling of openness rather than claustrophobic confinement. Inside, these modules would be divided into multiple levels, each serving a distinct purpose. The central and most protected areas would house the living quarters, research labs, and hydroponic gardens, the vital organs of the colony. The gardens would be particularly crucial, serving a dual role of producing food and recycling the atmosphere, with plants absorbing carbon dioxide and producing fresh oxygen. The outer layers of the habitat, nestled against the strong geodesic frame, might contain storage, power systems, and the intricate web of life support machinery that keeps the entire system running. Large viewports made from that same advanced, acid-resistant transparent material would offer breathtaking panoramic views of the endless cloud decks and the faint, shimmering sun above, a constant and awe-inspiring reminder of the incredible achievement this city represents. The true genius of this design is in its passive stability. Once a habitat is filled with breathable air and positioned at the correct altitude, it would require virtually no energy to maintain its position. It would simply float, anchored not to the ground but to a specific density layer in the atmosphere, a permanent resident of the Venusian sky. Small, efficient electric thrusters, powered by the abundant solar energy, would provide gentle propulsion for station-keeping, making minor adjustments to avoid drifting into less hospitable altitudes or to navigate closer to other habitat modules. This vision of a cloud city is not a constant struggle against a hostile world, but a masterful act of balance, a testament to human ingenuity in finding a way to not just survive, but to build a new home in the most unexpected of places. With our city in the sky designed and its life support secured, we come to the question of how to power this entire endeavor. This is where Venus transitions from being merely hospitable to being downright generous. The energy needs of a floating colony would be substantial, powering everything from air processors and water reclamation to computers, lighting, and propulsion. Thankfully, the very environment that makes this concept possible also provides an almost overwhelming abundance of power, turning a potential challenge into one of the project's greatest strengths. The most obvious and immense resource is solar energy. Venus orbits much closer to the Sun than Earth does, and at that 50-kilometer altitude, the colony will be positioned above the thickest, most opaque layers of the cloud deck. While the clouds do scatter a significant amount of light, they don't block it entirely. The environment would be one of perpetual, bright overcast, similar to a cloudy day on Earth. Crucially, the solar irradiance, the raw power arriving from the Sun, is nearly twice what we experience on our home planet. This means that a solar panel of the exact same size and efficiency would generate almost double the electricity when deployed above the Venusian clouds. This isn't a minor increase, it's a game changer. Vast arrays of solar panels could be mounted on the tops of the habitat modules, their surfaces treated with the same acid-resistant coatings to ensure longevity. These panels would soak up the intense, perpetual sunlight, generating more than enough power to meet the colony's baseline energy demands with incredible efficiency. But the Sun isn't the only source of power available in this dynamic environment. The upper atmosphere of Venus is a place of surprising movement, dominated by powerful, persistent winds. These are not the gentle breezes of Earth, but a phenomenon known as superrotation, where the entire atmosphere circles the planet at a ferocious speed, completing a full rotation in just 4 Earth days. While the habitats themselves would be largely carried along with this flow, creating the sensation of being in a slow-moving air current, the difference in wind speed between various atmospheric layers presents a massive opportunity. Engineers could deploy innovative wind turbines designed to capitalize on these powerful shear forces. Imagine specialized, durable turbines positioned around the periphery of the colony, their blades spinning from the relentless kinetic energy of the Venusian winds. This would provide a consistent and complementary source of power, ensuring electricity generation continues even during the Venusian night, which, though shorter than Earth's, still lasts for significant periods. This combination of solar and wind power creates a remarkably robust and renewable energy grid, one that is almost entirely independent of imported resources. The colony wouldn't need to worry about shipping up radioactive isotopes for nuclear reactors or manufacturing complex fuel cells. The planet itself would provide a constant, clean, and overwhelming flow of energy. This abundance doesn't just solve the problem of keeping the lights on, it opens up incredible new possibilities. With such a massive surplus of power, the colony could undertake large-scale industrial processes, from manufacturing building materials from processed atmospheric carbon to running energy-intensive research projects that would be impractical on Earth. This energy surplus could truly make a Venus cloud city not just an outpost for survival, but a powerhouse for scientific and industrial innovation, all fueled by the endless light and wind of its alien home. Of course, one of the most daunting questions about this entire concept has to be how we deal with the very thing that defines Venus's iconic appearance, those pervasive, beautiful, and highly corrosive sulfuric acid clouds. It's the planet's signature feature, and it represents perhaps the single greatest engineering obstacle to making a cloud city a reality. We are, after all, proposing to build a permanent home inside a mist of concentrated acid. This isn't a minor inconvenience, it's a constant, aggressive environmental threat that must be designed out of the equation from the very beginning. But here's the fascinating part: we are not starting from scratch. Humanity already has extensive experience designing machinery and materials to operate in highly corrosive environments right here on Earth, from chemical processing plants to offshore oil rigs constantly battered by salty, corrosive sea air. The challenge on Venus is greater, but the principles of defense are well understood. The first and most critical line of defense is the external cladding of the habitat itself, its skin. This material cannot be something standard like aluminum or untreated steel. It will be eaten away relatively quickly. Instead, engineers are looking at a suite of advanced passive materials that inherently resist acidic attack. Teflon, or more formally polytetrafluoroethylene (PTFE), is a prime candidate. You know it from your non-stick frying pan, but in its industrial form, it's an incredibly inert polymer, virtually impervious to strong acids and bases. An outer hull layered with or coated in Teflon-based composites would see sulfuric acid droplets simply bead up and roll off, causing no chemical reaction and no degradation. Beyond polymers, certain specialized ceramics and glass composites offer exceptional resistance and durability. Think of the tiles on the space shuttle, but designed for chemical rather than thermal extremes. Another promising avenue is the use of particular metal alloys, especially those rich in nickel and chromium, which form a protective, passive oxide layer that shields the underlying material from attack. The choice wouldn't be one single miracle material, but likely a cleverly engineered laminate combining the best properties of several. Perhaps a ceramic outer layer for hardness and durability, backed by a flexible acid-resistant polymer membrane, all bonded to a strong structural composite frame. This robust external shell creates a barrier, but a perfect seal is an impossible standard for any large, complex structure expecting to last for decades. The next layer of defense is therefore a positive pressure environment within the habitat. by maintaining the internal air pressure slightly higher than the external atmospheric pressure, you create a constant outward force. If a microscopic crack or flaw ever did develop in the outer hull, the flow of gas would be from the inside. Out our clean, breathable air would be slowly leaking into Venus's atmosphere, not the other way around. This prevents any corrosive vapors from ever being sucked inside, buying invaluable time for detection and repair. It's a simple but profoundly effective concept used in clean rooms and hazardous biological facilities on Earth. Inevitably, though, some external maintenance will be required. Solar panels will need cleaning, sensors will need adjustment, and the outer hull will need inspection. This is where technology takes over to minimize human risk. The majority of this work would be handled by robotics specially designed, ruggedized drones and rovers that can crawl along the exterior of the habitats, their joints and circuits sealed and protected, their optics made of acid-resistant sapphire glass. They would be the first line of inspection and repair, controlled remotely by operators safe inside. For tasks too delicate or complex for robots, humans would need to venture out in fully sealed exosuits. These wouldn't be the flexible pressure suits we use for spacewalks. They would be more akin to deep-sea diving suits or the armored outfits used in industrial asset handling. They would feature multiple layers of protective material, built-in acid washing systems to decontaminate the suit before re-entry, and would be tethered to the habitat for life support. The goal is to make external exposure a rare, meticulously planned event, not a routine part of daily life. By combining cutting-edge materials science with smart engineering controls and robotic workforce, the sulfuric acid clouds transform from an insurmountable barrier into a managed, calculated risk, one we already have the foundational knowledge to overcome. Now, let's step inside one of these incredible habitats and experience the view. Life in a Venusian cloud city would be defined by a visual environment utterly unlike any found on Earth. Forget a blue sky or a starry night. The world outside your window would be a perpetual, ethereal golden haze. The thick layer of carbon dioxide and sulfuric acid droplets high above the surface scatters sunlight in a unique way, bathing everything in a soft, diffuse, yellowish-orange glow. It would feel like living inside a beautiful, endless autumn sunset, a warm and constant light that never quite brightens to noon nor dims to true darkness. The sun itself would never be a sharp, defined disk you could look at. Instead, it would be a brighter, diffuse patch in the clouds, a luminous smear in the sky that moves almost imperceptibly slowly across the heavens. This leads to one of the most profound adjustments for any new resident, the Venusian day. A single rotation of Venus on its axis takes 116 Earth days. This means that from sunrise to sunset, you would experience roughly 58 Earth days of continuous, hazy daylight, followed by another 58 Earth days of a peculiar kind of night. But even this night wouldn't be truly dark. The dense, reflective cloud layer would create a lingering twilight effect for weeks, with the sky maintaining a deep, coppery luminescence long after the sun has set. Imagine 6 weeks of a gentle, golden afternoon, followed by 6 weeks of a deepening, amber twilight. This radical timescale would fundamentally reshape daily life, from work schedules and sleep cycles to agriculture and social rituals, all syncing to a rhythm dictated by a sun that seems to stand still in the sky. Yet for all its slow pace, the Venusian sky would put on a show of unparalleled beauty twice every 116 days, the sunrise and sunset. And these would be events in the truest sense of the word, each one lasting for hours. Because the sunlight has to pass through such a deep and complex atmosphere, the scattering of light would create a palette of colors we can scarcely imagine. You wouldn't see a quick dip below the horizon. You'd witness a slow, majestic transformation of the entire sky. The perpetual yellow-orange would gradually deepen into intense shades of copper, then burnished gold, and finally into rich, fiery crimsons and ambers that would swirl and shift for hours on end. It would be a spectacle of light that unfolds with the patience of a ballet, a daily reminder of the breathtaking and alien beauty of the world these pioneers have chosen to call home. This isn't just a view, it's a constant living work of art, a reward for daring to build a civilization in the clouds. But before we can stroll through those breathtaking golden vistas, we have to solve a very practical, down-to-earth problem. How do you actually get there, and just as importantly, how do you get back? The journey itself offers a fascinating mix of advantages and puzzles that make Venusian travel uniquely compelling. While Mars has captured the public imagination as humanity's next destination, a trip to the clouds of Venus presents a surprisingly more efficient initial journey. A direct flight to Venus can take as little as 100 to 150 days, often less time than a typical transit to the red planet, and it requires significantly less propulsion energy to escape Earth's gravity well and enter a transfer orbit toward the inner solar system. The real magic, however, happens upon arrival. Unlike Mars, which has an atmosphere too thin to be of much help, Venus comes with a built-in braking system, its incredibly dense, expansive atmosphere. This allows for a maneuver called aerobraking, a technique we already use for some of our orbiters. Instead of firing powerful and heavy retro-rockets to slow down and achieve orbit, a spacecraft bound for Venus would simply dip a carefully calculated amount into the upper layers of its atmosphere. The sheer density of the air creates immense drag, frictionlessly scrubbing off tremendous speed without using a single drop of fuel. The ship would essentially use the planet's own atmosphere as a brake pad, allowing it to slow down enough to be captured by Venus's gravity and settle into a stable orbit. This process isn't just efficient, it's a game changer, drastically reducing the amount of fuel a mission needs to carry from Earth and making the arrival procedure far less complex and risky. The greater and more novel challenge isn't landing, but rather launching from a city floating 50 kilometers high. How do you get from a floating platform back into space? This is where engineering creativity truly shines. One of the most promising concepts involves a specialized vehicle often called a Venusian spaceplane. Imagine a sleek, winged craft designed not for a runway but for the unique conditions of the upper atmosphere. This vehicle would be carried by its large wings, using the dense CO2 air for lift, much like an airplane on Earth. It would accelerate along a track on the habitat using powerful electric or chemical thrusters, lift off from the cloud deck, and then continue to climb through the thick atmosphere, gathering speed and altitude. Once it reached the uppermost, thinnest layers of the atmosphere, it would fire its onboard rockets to make the final push into orbit, rendezvousing with a waiting station. The thick atmosphere provides a long, powerful runway for gaining the necessary velocity, making the energy required for this final rocket burn much lower than a launch from Earth's surface. Another, even more visionary concept involves leaving rocketry behind almost entirely, a Venusian space elevator. This sounds like pure science fiction, but the physics at this altitude are surprisingly favorable. A space elevator requires anchoring a cable to a stable platform and extending it upwards to a counterweight in geostationary orbit. On Earth, this is nearly impossible because our geostationary orbit is over 35,000 kilometers away, requiring a cable of unimaginable strength. Venus, however, rotates very slowly. A spacecraft parked in a stationary orbit above a floating cloud city would be much, much closer, only about 50,000 kilometers above the platform instead of the planet's surface. While still a monumental engineering challenge, the required cable length would be significantly shorter than an Earth-based elevator. A climber vehicle powered by solar energy beamed from the colony could then glide up this carbon nanotube ribbon, ascending gracefully out of the atmosphere and into the vacuum of space without any explosive launches or high G-forces, transforming a dramatic launch into a serene, elevator-like ride to orbit. Now, with the mechanics of arrival and departure sorted, we arrive at the most human element of this grand endeavor. How do we feed ourselves? A colony cannot thrive on ration bars and shipments from Earth. True sustainability means learning to grow our own food, to create a self-sufficient biosphere floating in an alien sky. This challenge pushes us toward one of the most elegant and efficient forms of agriculture ever developed, perfectly suited to the constraints of a sealed environment, closed-loop aeroponics. Picture a dedicated module within the cloud city, a vast multi-level chamber that feels less like a farm and more like a cathedral of life. There are no fields of soil here, no tractors, no unpredictable weather. Instead, rows of plants are suspended in air, their roots misted with a nutrient-rich solution in a perfectly controlled environment. This is aeroponics, and it's a dream for space-based agriculture. It uses a fraction of the water required by traditional farming, and because the roots are exposed to oxygen, plants often grow faster and are less susceptible to disease. Every variable temperature, humidity, carbon dioxide levels, and nutrient composition is meticulously managed by computers to create the absolute ideal conditions for growth. And with no pests to worry about, there's no need for pesticides. The food produced wouldn't just be sustainable, it would be incredibly clean and nutritious. The light for this agricultural heart would not come from the golden haze outside, but from high-efficiency LED arrays tuned to specific spectra that optimize photosynthesis. Plants don't need the full spectrum of white light we see. They primarily use blue and red wavelengths. By providing just the light they need, these farms operate with maximal energy efficiency, a crucial consideration even with Venus's abundant solar power. The result is a surreal and beautiful sight. Vibrant green lettuce, plump tomatoes, and sweet strawberries thriving under a soft magenta glow, a stark and life-affirming contrast to the monochrome yellow world outside the viewports. But a truly closed-loop system means nothing goes to waste. Every scrap of organic material, plant trimmings, inedible stems, and of course human waste is not discarded. It is a valuable resource. These materials would be processed in bioreactors, where carefully selected strains of bacteria would break them down, recovering the water and converting them back into basic nutrients. These reclaimed nutrients are then fed directly back into the misting systems, completing the cycle. Water, the most precious commodity of all, is endlessly purified and recycled through this same process, with every drop of moisture from transpiration and even the humidity in the air itself being captured and returned to the system. This creates a near-perfect ecological loop, mimicking the cycles of nature on Earth, but with a level of precision and efficiency that our home planet never achieves. The benefits of this sky-born garden extend far beyond the dinner plate. These plants are the colony's primary life support system, the literal lungs of the habitat. Through photosynthesis, they consume the carbon dioxide we exhale and generate the fresh oxygen we need to breathe. They are a living, growing machinery of air revitalization, far more graceful and psychologically comforting than a sterile metal tank of compressed gas. And this touches on perhaps their most vital role, psychological well-being. Living inside an entirely human-made environment, surrounded by metal and composite materials and gazing out at an alien sky, could become mentally draining over time. These lush green spaces provide an essential connection to Earth, a place of tranquility and natural beauty. The scent of moist soil and growing plants, the simple act of tending to a crop, the color green. These are profound comforts, offering a necessary reminder of the world we came from and a tangible symbol of the new life we are building millions of miles away. And just as we've learned to draw breathable air from the toxic Venusian sky, the next monumental challenge becomes sourcing the very essence of life itself, water. It's the fundamental ingredient for our survival, crucial not just for drinking, but for growing food, for humidity control, and as a vital component in countless industrial processes. On a planet whose surface is a scorching, waterless desert, this might seem like an insurmountable obstacle, but the solution, once again, is hidden in plain sight, suspended within the atmosphere we aim to call home. The upper cloud decks of Venus are not composed of pure water vapor, but they do contain a surprising amount of the raw building blocks needed to create it. A primary constituent of those infamous clouds is sulfuric acid, H2SO4. While that sounds incredibly hostile, and it is, to a clever chemist, it's not just a problem to be mitigated, it's a potential reservoir. Through a process called chemical decomposition, we can break sulfuric acid down into its constituent parts. By applying energy and the right catalysts, we can split each molecule of sulfuric acid into sulfur trioxide, SO3, and water, H2O. It's a process that effectively turns the planet's greatest atmospheric threat into its most vital life-saving resource, transforming the corrosive clouds into a literal wellspring. This isn't a simple or low-energy task, of course. It would require sophisticated processing facilities, likely using a method similar to the contact process employed in industrial chemistry on Earth, but in reverse. Imagine intakes on the outside of the habitat carefully collecting the acidic mist. This slurry would then be fed into reaction chambers where heat and catalytic surfaces, perhaps made of platinum or vanadium pentoxide, would facilitate the breakdown. The sulfur trioxide byproduct could be further processed and stored. It might even become a useful industrial chemical for the colony down the line. The water vapor produced would then be condensed, purified through multi-stage filtration, and sent into the colony's closed-loop water system. It's a brilliant piece of chemical engineering that turns a liability into an asset. But sulfuric acid isn't the only potential source. While Venus has no surface oceans, its atmosphere does contain trace amounts of water vapor. The concentration is very low, estimated to be only around 20 parts per million, but the sheer volume of the atmosphere is so immense that even this tiny percentage represents a vast total quantity of water. Extracting it would be a feat of large-scale engineering, using massive arrays of specialized absorbers or condensers that cool vast quantities of atmosphere to wring out every last precious droplet. It would be like harvesting morning dew on a planetary scale, a slow and steady trickle that could supplement the primary production from sulfuric acid processing. The energy required for all this would be significant, but it circles back to Venus's greatest gift, abundant solar power. The same intense sunlight that bathes the cloud cities can be harnessed to power the electrolysis, the heating chambers, and the condensation systems needed to liberate water from the acidic air. This creates a beautifully synergistic cycle. The sun provides the power to crack the acid provides the water, and the water sustains the life that enables the entire endeavor. It's a testament to the fact that living on another world isn't about finding a place that's exactly like Earth. It's about understanding the resources a new world does offer and mastering the technologies needed to reshape them into the things we need to survive and ultimately to thrive. However, this gentle buoyancy exists within a much larger, more dynamic system, a planet-wide river of air moving with unimaginable force. The upper atmosphere of Venus is dominated by a phenomenon known as superrotation, a term that hardly does justice to the sheer power it represents. While the planet itself rotates at a sluggish pace, taking 243 Earth days to complete a single spin, its atmosphere has a mind of its own. At the altitude of our proposed cloud cities, the entire sky is a continuous, raging hurricane, with winds screaming around the planet at speeds of up to 360 kilometers per hour. To put that in perspective, that's faster than the most powerful Category 5 hurricane ever recorded on Earth, and this isn't a temporary storm. It's the permanent, unending state of the Venusian sky, a perpetual jet stream that circumnavigates the entire globe once every 4 Earth days. Living within this immense atmospheric river would be a masterclass in harnessing nature's power rather than fighting it. The colonies wouldn't fight these winds, they would become a part of them, designed to move with the flow. Think of them not as stationary buildings, but as the most magnificent, sophisticated dirigibles ever conceived, sailing upon this global current. Their primary design goal would be stability within the stream, not resistance to it. The concept of being anchored to a specific geographic location, like a city on Earth, becomes irrelevant when the entire atmosphere you live in is moving in a coherent, predictable band. Your address wouldn't be a set of coordinates on a map, but a specific altitude and density layer within a planet-wide weather system. Navigation between different habitat modules would be less about traveling vast distances and more about making precise altitude adjustments to catch slightly different wind currents, allowing for a graceful, energy-efficient dance through the clouds. A primary engineering challenge shifts from dealing with gusty, unpredictable turbulence, which is minimal in this steady, laminar flow, to managing shear forces. While the overall wind speed is incredibly high, the difference in speed between various layers of the atmosphere is what creates potential hazards. A habitat must maintain its position within its designated sweet spot with extreme precision. Drifting too high or too low could subject it to powerful shearing winds that could stress the structure. This is where those small, efficient electric thrusters come into play, performing constant minor adjustments to maintain altitude and attitude, ensuring the colony rides the smoothest part of the atmospheric river. And this relentless wind, rather than being just a challenge to overcome, presents one of the colony's most reliable power sources. The kinetic energy roaring past the habitats is nothing short of monumental. Engineers could deploy specialized, ruggedized wind turbines unlike anything on Earth. These wouldn't be the towering, three-bladed turbines we're familiar with. They would likely be more compact, ducted, or vertical axis turbines designed to efficiently extract energy from the high-speed, dense air without creating excessive drag on the habitat itself. Positioned strategically around the exterior of the city, these turbines would spin ceaselessly, generating a constant and massive supply of electricity. This wind power would be the colony's workhorse, providing base load power day and night, complementing the solar arrays that generate peak power during the long daylight periods. This combination ensures an uninterrupted, abundant energy supply, turning the planet's most formidable weather feature into its most generous utility, powering the dream of life among the clouds. This radical new environment would fundamentally reshape the very fabric of human society. The first generations to call the Venusian clouds home, the true pioneers, wouldn't just be adapting to a new planet. They would be consciously architecting a new social order from scratch within a completely controlled and finite environment. The constraints of living in a floating city, where every breath of air and square meter of space is a precious engineered resource, would force a level of cooperation and collective purpose far beyond anything we experience on Earth. This wouldn't be a frontier town where you can simply build another shack on the outskirts. The very structure of the habitat would physically embody the social contract its inhabitants agree to live by. The initial founding structure would likely dictate the colony's long-term character. Would it be a tightly controlled scientific outpost, run like an Antarctic research station with a clear hierarchy focused on specific research goals? Or would it be a corporate venture, established to mine the atmosphere for rare elements or to develop new technologies, where productivity and profit become the central tenets of daily life? Perhaps the most fascinating possibility is a purpose-built society, founded by a group with a specific philosophical or cultural vision, seeking to implement a new model of governance, economy, and community far from Earth's established systems. Each model brings its own strengths and challenges. A scientific outpost offers clear goals and structure but might struggle with long-term livability. A corporate venture could be incredibly efficient but risks creating a stratified company-town dynamic. A visionary society could be inspiring and innovative but also vulnerable to ideological strife. In reality, the first cloud city would likely be a hybrid, a pragmatic blend of scientific necessity, economic reality, and the undeniable human desire to build something meaningful. Psychologically, life would be a profound balancing act. The constant, breathtaking view of the endless golden haze is undeniably beautiful, but it is also a permanent reminder of absolute isolation and the lethal fragility of your existence. There is no stepping outside for a walk, no feeling of rain on your skin, no connection to a natural world beyond the transparent alloy of the viewport. This could lead to a phenomenon akin to what submariners or long-duration astronauts experience, a form of cabin fever magnified by the surreal and unchanging landscape. The lack of natural circadian rhythms with a day-night cycle that lasts for months would require artificial lighting systems to regulate sleep patterns and prevent widespread depression. The community would have to be intensely mindful of mental health, making communal spaces the absolute heart of the habitat. These wouldn't be luxuries, they would be critical infrastructure. Imagine vast, multi-level atriums designed not just for congregation, but for psychological respite. These would be lush, green oases filled with the sights and sounds of earth, trees, flowering plants, running water, and even projected images of blue skies and forests. They would serve as the town square, the park, and the communal living room all in one, a place to socialize, to relax, and to momentarily forget the alien world outside. In such a confined environment, the line between public and private life would blur, making these shared spaces essential for reducing social friction and fostering a strong sense of community identity and mutual support. To combat the sensory monotony and the distance from Earth, virtual reality would evolve from an entertainment medium into an essential tool for sanity and connection. Through VR, a colonist could take a walk on a beach, visit a bustling city on Earth, or even experience the illusion of vast, open landscapes. It would be a vital window to the world they left behind and a creative outlet for art and expression. More importantly, it would provide a necessary sense of privacy and personal space in a community where physical solitude is a rare commodity. The society that thrives in the clouds of Venus won't be the one with the most advanced air processors or the strongest alloys, though those are crucial. It will be the one that most successfully masters the human element, building a culture that values psychological well-being, fosters deep communal bonds, and finds a new definition of home among the stars. Of course, a permanent human presence in the clouds of Venus must be more than a breathtaking feat of engineering or a scientific observatory. To be truly sustainable across generations, it needs a robust economic engine. It needs to produce value that justifies the immense initial investment and ongoing support, creating a society that is not just surviving, but actively thriving and growing. The question of what people would actually do there every day is central to the entire vision, and the answers are as fascinating as they are varied, rooted in the unique advantages the Venusian environment provides. The most immediate and powerful economic driver would undoubtedly be pure, unparalleled science. Venus is a natural laboratory for studying planetary science and climatology on a scale impossible to replicate anywhere else. Think of it as a massive, real-world model for understanding runaway greenhouse effects. By studying the intricate chemical processes, atmospheric dynamics, and energy balance of Venus in real time, scientists living there could unlock secrets that are critically important to us here on Earth, providing invaluable data to refine our climate models and perhaps even develop future geoengineering strategies. Furthermore, the position of a cloud city offers a phenomenal platform for astronomy. Perched high above the most opaque, light-distorting layers of the atmosphere, a telescope based here would have a crystal-clear view of the cosmos, unimpeded by the turbulence and pollution that challenges even the best Earth-based observatories. It could peer into the depths of space, studying distant galaxies, exoplanets, and cosmic phenomena with a clarity that rivals the James Webb Space Telescope, but with the distinct advantage of being serviceable by human technicians on site, allowing for upgrades and repairs that are impossible for a distant satellite. Beyond observing the cosmos, the colony itself would become a hub for pioneering new technologies. The relentless need to solve problems, from creating acid-resistant materials and perfecting closed-loop life support to managing energy in a high-radiation environment, would spur incredible innovation. Technologies first proven in the extreme laboratory of Venus would inevitably filter back to Earth, leading to advances in corrosion-proof coatings, ultra-efficient water reclamation systems, advanced robotics, and new forms of renewable energy generation. A Venusian cloud city could effectively become a self-funding research and development center, its very existence pushing the boundaries of human capability and selling the patents and licenses for its breakthroughs back to an eager terrestrial market. Then there's the more speculative but tremendously exciting possibility of resource extraction. While the surface is forbidding, the atmosphere itself is a vast chemical reservoir. We've already discussed mining it for breathable air and water, but it may contain other valuable compounds. The sulfuric acid clouds are a potential source of sulfur itself, a critical element in many industrial processes and fertilizers. More intriguingly, some theories suggest that the lower atmosphere, closer to the superheated surface, could contain trace amounts of rare or precious elements vaporized from the rocks below. Imagine a future industry not of traditional mining, but of atmospheric filtration, using autonomous, heavily shielded drones that dive into the deeper, hotter layers to collect samples or even siphon valuable gases, returning them to the processing plants in the temperate cloud layer. These resources wouldn't necessarily be shipped back to Earth. The energy cost of escaping Venus's gravity makes that impractical for bulk materials, but they could be used to support the colony's own expansion and manufacturing, making it increasingly self-sufficient and creating an internal economy based on refining and construction. This points toward a long-term economic model that is less about exporting physical goods and more about exporting knowledge, data, and technological solutions. The primary exports of Cloud City might be groundbreaking scientific papers, incredibly detailed planetary climate data, patents for unbelievably durable materials, and the operational blueprints for building a self-sustaining civilization in a hostile environment, a skill set that would prove priceless as humanity looks toward settling other worlds. The economy would be built on intellect and innovation, making a floating metropolis on Venus not just a strange outpost, but potentially one of the most valuable and intellectually productive real estates in the entire solar system. So, after exploring the incredible possibilities of life above Venus, it's only fair to return to that fundamental question that probably sparked in your mind the moment this concept was introduced. Why choose the acidic clouds of Venus over the rusty, rocky plains of Mars? This isn't just a casual debate. It's a critical discussion about the two most viable pathways for humanity's expansion into the solar system. And each destination offers a radically different vision of our future, with a unique set of profound advantages and daunting challenges. It's less about declaring a single winner and more about understanding which set of problems we, as a species, are better equipped and more willing to solve. Let's break it down, starting with the undeniable, fundamental advantages that Venus holds. First and foremost is gravity. Venus, as our sister planet in size, provides a gravitational force about 90% of Earth. This is a monumental factor for long-term human health that is often overlooked in the excitement about Mars. On the red planet, with just 38% of Earth's gravity, we know that astronauts will face severe bone density loss, muscle atrophy, and potential cardiovascular issues that could make a return to Earth permanently damaging. A child born and raised on Mars might never be able to visit their ancestral homeworld. On Venus, however, we could live, work, and raise families under a gravitational force nearly identical to what our bodies evolved for, preserving our health and ensuring a much more normal human experience for generations to come. Then there's the matter of inherent safety. Mars is a radiation-soaked desert, its surface bombarded by solar and cosmic rays due to its thin atmosphere and lack of a global magnetic field. Living there means living underground or inside heavily shielded habitats to avoid dangerous exposure. Venus, by contrast, comes with a built-in radiation shelter. Its incredibly dense atmosphere provides a phenomenal natural shield. At that 50-kilometer altitude, the radiation exposure is comparable to living on Earth, meaning our floating habitats wouldn't need complex, heavy, and energy-intensive shielding. The planet itself does that job for us for free. Furthermore, the atmospheric pressure at that altitude is almost exactly one Earth atmosphere, eliminating the risk of explosive decompression that constantly threatens habitats on airless worlds like Mars or the Moon. Now, let's look at the Martian perspective, which is built on a more familiar, tangible foundation. The greatest psychological and practical advantage Mars offers is solid ground. There is an undeniable comfort and simplicity in building on a stable surface, even if that surface is alien. We can use traditional construction methods, anchor structures to the ground, and mine local resources like regolith for building materials and radiation shielding. This feels more intuitive, more like the frontier settlements of Earth's past. Mars also offers a day-night cycle that, while slightly longer than Earth's at 24.5 hours, is far more familiar and manageable than the months-long day and bizarre, protracted twilight of Venus. This natural rhythm is easier on our biological clocks and simplifies agriculture and daily life. Access to surface resources is another key point for Mars. While its atmosphere is thin, it is mostly carbon dioxide, which can be processed for oxygen and methane fuel. Water ice is abundant at the poles and likely in subsurface deposits across the planet, providing a critical resource for life support and fuel production. The solid surface also means that if something breaks, you can send a rover or an astronaut in a suit to physically fix it. A straightforwardness that is appealing compared to performing external repairs while floating in a corrosive, super-rotating atmosphere. Ultimately, this debate frames two distinct visions. Choosing Venus is about embracing a high-tech, closed-loop existence. It's a commitment to mastering advanced material science, atmospheric processing, and living in a meticulously engineered environment where the very air you breathe is also the foundation beneath your feet. The reward is a more Earth-like physical experience in terms of gravity and pressure, situated in a breathtaking, if surreal, sky world. Choosing Mars is about a more traditional, albeit still incredibly difficult form of pioneering. It's about rooting ourselves in alien soil, exploring vast canyons and mountains, and dealing with challenges of low gravity and radiation that feel more direct and mechanical. One path isn't inherently better than the other. They simply appeal to different aspects of the human spirit, the elegant engineer versus the gritty explorer. In the long run, humanity will likely pursue both, creating a diverse and resilient interplanetary future. But the first step will define our initial priorities and test our ingenuity in ways we are only beginning to imagine. Given the sheer scale of the ambition, it's natural to wonder just how far away this future truly is. Are we talking about a project for our grandchildren, or could we see the first steps in our own lifetimes? The answer is a fascinating blend of near-term reality and long-term vision, and it's being shaped by some of the brightest minds at NASA and other space agencies right now. This isn't relegated to the whiteboards of science fiction writers. It's the subject of serious scientific and engineering studies, the most famous of which is NASA's own high-altitude Venus operational concept, or HAVOC. HAVOC represents the crucial first phase of making this dream a reality. It's not a plan for a city, but rather a proof-of-concept mission, a bold initial foray into the Venusian atmosphere. The concept involves sending a crewed mission to spend 30 days orbiting the planet, followed by a descent into that habitable cloud layer. The crew would travel in a mothership that remains in orbit, while a smaller, specialized blimp-like aerostat vehicle and a habitation capsule would be deployed into the atmosphere. The astronauts would transfer to this floating outpost, living and working within it for up to a month, conducting groundbreaking science and proving every critical technology needed for long-term survival: atmospheric processing, power generation from solar arrays, and operations in that corrosive environment. This 30-day mission would be the Apollo program for Venus, demonstrating that human presence is not only possible but also immensely valuable. Building on that, the logical next step would be establishing a permanent but initially uncrewed automated outpost. Imagine sending a fleet of robotic builders ahead of any human settlers. These advanced machines would descend into the atmosphere, link up, and begin the autonomous construction of the first full-scale habitat module. They would activate the life support systems, start the atmospheric processes creating a breathable air supply, and grow the first hydroponic gardens, all while being remotely monitored from Earth. This self-building, self-checking outpost would sit vacant, waiting for perhaps a year or more, ensuring every system is perfectly stable and sustainable before a single human ever sets foot inside. This method drastically reduces the risk for the first pioneers, who would arrive not to build their home from scratch, but to inhabit a new home that is already fully operational and waiting for them. So, when could we actually see this happen? A sprawling, permanent cloud city with families and a diverse economy is likely a project for the next century, an endeavor that will require international cooperation and sustained investment over decades. However, the groundbreaking steps to get there are much, much closer. A robotic scout mission to test materials and deployment mechanisms in the actual Venusian atmosphere could be launched within the next 10 to 15 years. A Havoc-style 30-day manned demonstration mission, while incredibly complex, is a conceivable goal for the 2040 to 2050 time frame. This isn't the distant future, this is a horizon within the view of many people watching this today. It means that the children born now could be the engineers designing those first habitats, or the scientists analyzing the first real-time data beamed back from a robotic outpost. The dream of life among the clouds of Venus is no longer pure fantasy. It's a formidable engineering challenge with a plausible, step-by-step roadmap, and its first chapter is waiting to be written by the current generation. The extreme challenges of building a permanent home in the clouds of Venus would force us to innovate at a pace and on a scale rarely seen in human history. But the incredible truth is that the vast majority of these technological breakthroughs wouldn't just be confined to a distant world. They would inevitably spin off, cascading back to Earth with the potential to revolutionize how we live, work, and manage our own planet's delicate environment. This isn't a secondary benefit, it's a core part of the value proposition, turning a mission of exploration into a direct investment in solving some of our most pressing terrestrial challenges. Perhaps the most immediate and impactful area of innovation would be in the development of super-corrosion-resistant materials. To survive the sulfuric acid clouds, we would need to pioneer new alloys, ceramics, and polymer coatings with an almost magical ability to shrug off chemical attack. These wouldn't be laboratory curiosities. They would be production-ready, ultra-durable materials tested in the most unforgiving environment imaginable. The applications back on Earth would be transformative. Imagine bridges, ships, and offshore wind turbines coated with a Venus-proven material, effectively immune to the rust and decay caused by saltwater, acid rain, and pollution. The economic and environmental savings would be staggering, drastically reducing the need for constant repainting, repair, and replacement of critical infrastructure. Chemical processing plants, which currently use expensive and heavy specialized vessels, could operate more safely and efficiently with lighter, tougher components. Even everyday objects, from the frames of our cars to the pipes in our homes, could last for generations, profoundly reducing waste and resource consumption. Next, consider the radical advancements in closed-loop life support systems. A Venusian habitat is the ultimate testbed for sustainability, a perfectly sealed biosphere where every single molecule of water, every ounce of waste, and every breath of air must be meticulously tracked and recycled. The technology to achieve 100% water reclamation, pioneered for survival in an atmosphere with no free water, could be deployed in water-scarce regions on Earth. It could turn any wastewater from agricultural runoff to industrial effluent into pristine drinking water with near-total efficiency, addressing global water crises. The methods for processing human and organic waste into clean fertilizer and even food through advanced bioreactors and aeroponic systems could redefine agriculture, enabling high-yield farming in urban vertical farms with minimal water and no pesticides, drastically reducing the environmental footprint of feeding our population. The energy systems developed for a cloud city would be another game-changing export. While we have solar power on Earth, the need for maximum efficiency in a demanding environment would push the technology far beyond its current limits. We would see solar panels that are not only more efficient at converting sunlight, but are also incredibly lightweight, flexible, and durable. These next-generation panels could be integrated into the very fabric of our buildings, our vehicles, and even our clothing, making renewable energy ubiquitous and seamless. Furthermore, the advanced energy storage systems required to manage power through the long Venusian night would lead to breakthroughs in battery technology and perhaps novel methods like flywheel or thermal storage, solving the intermittency problem that currently hampers our full transition to renewables. This means more reliable green energy for our grids, making blackouts a thing of the past and accelerating our departure from fossil fuels. Finally, the entire philosophy of atmospheric processing, of learning to see a toxic environment not as a waste product but as a reservoir of valuable resources, is perhaps the most valuable lesson we could bring home. The technology to scrub carbon dioxide from the Venusian air and split it into breathable oxygen and useful carbon is essentially a supercharged version of the direct air capture systems we are only beginning to develop to combat climate change. Mastering this on Venus would provide us with a proven, scalable blueprint for actively reducing the greenhouse gas concentration in our own atmosphere. We could literally start mining the sky for carbon, turning a pollutant into a feedstock for manufacturing, building materials, and synthetic fuels. This transforms the fight against climate change from a story of sacrifice and limitation into one of active engineering and resource creation, offering a powerfully hopeful vision for planetary management. In this way, the quest to settle Venus becomes the greatest catalyst for technological and environmental progress on Earth. The challenges of that alien world force us to become smarter, more efficient, and more circular in our thinking. The technologies born from necessity in the clouds of Venus would empower us to build a more resilient, sustainable, and prosperous civilization right here at home, proving that the greatest reward of reaching for the stars might just be learning how to take better care of our own planet. But all of this incredible engineering and ambition leads us to a much deeper, more profound question that transcends the how and ventures directly into the should. As we stand on the precipice of becoming a multi-planetary species, we must pause and look beyond the blueprints and the physics to consider the ethical weight of our actions. Do we, as a species that has so profoundly reshaped our own world, have the inherent right to step onto another planet and begin the process of altering its environment to suit our needs, even if that world appears to be utterly lifeless? This isn't a question with an easy answer, and it forces us to confront our responsibility not just to ourselves but to the broader cosmos. On one hand, the human drive to explore and to settle new frontiers is undeniably a core part of our character. It's what propelled us across oceans and continents, and it's the same impulse that now looks to the stars. Proponents of colonization argue that spreading life is a fundamentally positive act, a way to ensure the survival of Earth's biological heritage against any number of potential catastrophes that could befall our single planet. From this perspective, transforming a dead world into a living one is the ultimate expression of creativity and stewardship, a project that could span centuries but would ultimately create a new branch of human civilization and perhaps even new forms of ecosystems. We wouldn't be mere visitors, we would be gardeners, carefully and deliberately cultivating a new home in a vast and mostly empty universe. The counterargument, however, urges profound caution. It asks us to consider the principle of planetary protection in its most strict form. Even though the surface of Venus is a hellscape, we cannot say with 100% certainty that the cloud layers themselves are completely sterile. On Earth, we find extremophile bacteria thriving in the upper atmosphere, feeding on dust and minerals carried by the wind. The possibility, however remote, that similar microbial life could have adapted to the acidic environment of Venus's clouds cannot be entirely dismissed. If such life does exist, however simple, our arrival would represent an unprecedented planetary invasion. Our Earth microbes, hitchhiking on every component of our habitats, could outcompete and drive any native organisms to extinction before we even had a chance to discover them. This wouldn't just be an ecological disaster, it would be a cosmic tragedy, the irreversible loss of a second genesis of life, a unique chapter in the story of the universe that we erased before we even learned to read it. This brings us to the critical, practical protocols of contamination. The science of ensuring we don't bring Earth life to other worlds, called forward contamination, and vice versa, called back contamination, is already a well-established field for Mars missions. But for Venus, the protocols would need to be even more extreme and innovative. Every single component of a cloud city, from the largest habitat module to the smallest screw, would need to be assembled in a sterile environment on Earth and subjected to microbial reduction techniques far beyond what we currently practice, perhaps using intense radiation or heat sterilization. The habitats themselves would need to be designed as near-perfect biological bubbles, with sophisticated airlocks and decontamination chambers for any equipment or people moving between modules. It would require a constant, vigilant monitoring program, scanning the external atmosphere for any sign of biological activity and rigorously checking the interior for any escape of Earth organisms. This level of planetary hygiene wouldn't be optional. It would be the foundational ethical guideline for the entire mission, a non-negotiable commitment to preserving the scientific and existential integrity of another world. Ultimately, the question of whether we should colonize Venus is not a binary yes or no, but a mandate to proceed with humility, transparency, and an overabundance of caution. It compels us to elevate our ambitions beyond mere survival and expansion, challenging us to become a species that explores not as conquerors but as conscientious guests. The protocols we develop and the international agreements we forge will set a precedent for all future interactions with other worlds, defining our role in the solar system for generations to come. It's a conversation that needs to include not just scientists and engineers, but philosophers, artists, and the global public, because the decision to plant a flag in the clouds of Venus isn't just about claiming a new territory. It's about defining the very character of our civilization as we take our first tentative steps into the cosmic ocean. Yet this vision of a self-contained city in the sky only captures a fraction of its true potential. Its greatest role may not be as a final destination, but as a central hub, a bustling interplanetary port that unlocks the entire solar system for humanity. Positioned closer to the Sun, a Venusian cloud city occupies a location of incredible strategic value, making it the perfect stepping stone and refueling depot for voyages into the deeper reaches of space. Think of it as a grand cosmic harbor where great ships from Earth could dock, resupply, and prepare for the long journey outward, all while utilizing the planet's own physics to save immense amounts of time and fuel. The first and most powerful advantage is the gravity assist or slingshot maneuver. This is a technique we already use with our robotic probes, but with a permanent station at Venus, it becomes a routine and supercharged operation. Here's how it works. A spacecraft from Earth would aim not directly for the outer planets, but for a precise rendezvous with Venus. As it swings around the planet, it gets a powerful gravitational tug, a sort of celestial crack of the whip that flings it away at a much higher velocity than it arrived with. This maneuver effectively allows ships to borrow a tiny bit of the planet's orbital momentum, granting them a massive boost in speed without burning a single drop of their own fuel. For missions headed to the asteroid belt, Jupiter or Saturn, this Venusian slingshot could cut months off the travel time and reduce the propellant needed at launch from Earth, making these ambitious journeys far more efficient and feasible. But the benefits extend far beyond a simple gravity boost. After completing this maneuver, a ship wouldn't just fly onward into the void. It could dock at one of the orbital stations serviced by the Cloud City below to undergo a complete resupply. This is where the colony's resource production becomes a game changer for the entire solar system. Imagine a freighter from Earth arriving with a hold full of specialized machinery or delicate instruments. It docks at the Venus orbital station, and instead of needing to carry all the propellant, water, and oxygen for its entire multi-year mission to the moons of Jupiter, it can simply refill its tanks right there. The Cloud City below would have industrial-scale plants dedicated to cracking carbon dioxide from the atmosphere into oxygen for breathing, and when combined with hydrogen shipped from Earth or extracted from water, into methane rocket fuel. This means that the most massive and consumable components of space travel, the very things that make it so expensive to launch from Earth, can be manufactured on site in space at a fraction of the energy cost. This transforms the economics of solar system exploration. Rather than every single mission to the outer planets being a colossal, one-shot effort launched at tremendous expense from Earth, they can become more like oceanic voyages. A ship launches from Earth with its core crew and mission-specific cargo, travels to the Venusian way station, and tops off all its consumables, fuel, water, air, and even fresh food from the aeroponic farms. It then uses the Venus slingshot to catapult itself on its way, arriving at its distant destination with full tanks, allowing for more maneuvering, longer stays, and greater scientific returns. On its way back, it could even stop at Venus again to resupply before the final leg home. This creates a sustainable transportation network, with Venus acting as the central tavern and garage along the cosmic highway, enabling a frequency and scale of exploration that is simply impossible if every journey must begin and end solely on Earth. It shifts our entire paradigm from launching missions to establishing routes, turning the solar system from a distant frontier into a connected, accessible neighborhood. Waking up on Venus is a gentle affair, the slow brightening of the ambient golden light in your quarters signaling the beginning of another long, hazy day. There's no sudden alarm, no jarring burst of sunlight, just the gradual shift from a deep copper gloom to a warm, pervasive amber glow. You stretch in the comfortable Earth normal gravity, a luxury not afforded to settlers on other worlds, and your first conscious act is to glance at the large viewport that makes up one entire wall of your room. The vista is unchanging yet endlessly captivating, a sea of swirling, saffron-tinted clouds stretching to a soft, indistinguishable horizon, a perpetual and serene landscape that defines existence here. The only sound is the low, constant hum of the life support systems, a soothing white noise that is the habitat's steady heartbeat. Breakfast is a testament to the colony's self-sufficiency. The food isn't from a freeze-dried packet or a recycled protein paste, it's fresh. You slice a deep red tomato and some crisp greens, all harvested just hours ago from the aeroponic farms a few modules away. The eggs from the small avian species bred for both protein and pest control in the gardens are fluffy and rich. This isn't just sustenance, it's a daily ritual that connects everyone to the delicate, human-made biosphere that keeps them alive. The coffee, a prized luxury, is grown in a dedicated horticulture dome and is perhaps the most talked about commodity in the entire city. A rich, robust flavor that colonists swear is better than any on Earth, its cultivation a point of immense pride. The commute to work is a journey through the city's arteries. You don a light jacket, the interior climates are carefully regulated, but some corridors are cooler than others, and step out into a broad, circular concourse. There are no cars here. Personal transport is a network of silent, electric trams and moving walkways that glide between the interconnected habitat spheres. The sky above the concourse is a high, vaulted ceiling projecting a soft, blue-hued light spectrum designed to maintain circadian rhythms, a welcome visual break from the yellow outside. You pass others on their way to their shifts, botanists heading to the farm modules, engineers adorned with tool harnesses, a group of children shepherded by an android facilitator towards the learning center. There's a quiet, purposeful energy, a sense of shared mission. Your own work takes place in a climatology research lab, a sphere whose exterior wall is a single, seamless pane of advanced transparent ceramic. The view is your primary instrument. You and your team are tracking the dynamics of the super-rotation below, monitoring the vast, slow-moving storm systems that rage within the cloud layers. The data streaming across your screens is complemented by the direct observation of immense cloud formations swirling past, their structures illuminated by your station's external light. The work is painstaking, but its implications are profound, helping to refine the predictive models that keep the entire city safely riding the atmospheric currents. Leisure is not a luxury here, it's a critical component of psychological maintenance. After your shift, you meet friends in Central Park, the social and ecological heart of the colony. It's not a park of grass and soil, but a magnificent multi-level atrium filled with the vibrant green of genetically engineered plants and the gentle sound of recycled water flowing over artfully arranged rockeries. The air here is different, thick with the humid, fertile scent of earth and growing things, a fragrance that is a powerful antidote to the sterile, recycled atmosphere of the living quarters. This is where the community gathers to talk, to play games on manicured synthetic turf, or simply to sit on a bench and be surrounded by the color green, a vital psychological tether to the world 50 million kilometers away. As the interminable day finally begins its slow wane into a weeks-long twilight, you find a quiet spot in an observation lounge. The sunset on Venus is not a quick affair, it is a majestic, hours-long spectacle. The perpetual golden haze deepens into breathtaking shades of burnished copper, then fiery crimson, and finally into a profound, luminous amber that seems to set the very clouds ablaze from within. You watch this silent, awe-inspiring display with a handful of other colonists, no one speaking, everyone connected by the shared experience of witnessing a beauty that is utterly alien and yet profoundly moving. It's a daily reminder of the audacity of their home, a bubble of life and warmth adrift in a magnificent, unforgiving sky, and the quiet pride of calling such an impossible place home. Yet for all its carefully managed systems and elegant engineering, life floating in the Venusian sky would never be without its perils. We've talked about the obvious threats, the corrosive clouds, the immense pressures below, but the true test of this civilization would come from the unexpected, the hidden risks that lurk within the planet's complex and dynamic atmosphere. Imagine the unsettling sound of an alarm cutting through the gentle hum of the life support systems, a high-pitched tone signaling a pressure anomaly. A microscopic fracture, perhaps caused by a micrometeorite too small for radar to track, or a flaw in a seal stressed by years of acidic exposure, has developed in an outer utility corridor. The immediate danger isn't an explosive decompression, thanks to the near-equal external pressure, but something more insidious, a slow, steady leak of breathable air. Because the internal atmosphere is our lifting gas, even a small leak is a dual crisis. You're not just losing the air you breathe, you're losing your buoyancy, the very thing keeping you aloft. The colony's automated systems would be the first responder, sealing off the compromised section with blast doors and activating local compressors to pump in stored air, fighting to maintain both pressure and lift. Repair crews, clad in their heavy, acid-resistant exosuits, would have to venture into the isolated, potentially contaminated section to find and patch the breach, working against the clock as monitoring screens track a gradual, terrifying descent of mere meters per hour. It's a silent, relentless battle against a loss of integrity, where every molecule of air lost is a step closer to the inferno below. Then there's the threat from above. While the thick atmosphere provides a superb shield against cosmic radiation, it would offer little defense against the electromagnetic pulse of a major solar flare. A coronal mass ejection from the sun, arriving with relatively little warning, wouldn't fry the colonists with radiation, but it would unleash a devastating power surge through the colony's extensive external networks. The vast solar arrays, the wind turbines, and every sensor and communication dish on the exterior would be hit by a wave of energy that could instantly overwhelm and fry delicate circuitry. The real nightmare scenario is a complete electrical blackout. Without power, the air processors stop, the lights go out, and most critically, the electric thrusters used for station keeping go silent. Drifting powerless in the super-rotating atmosphere, the colony would be at the mercy of Venus's most terrifying meteorological phenomenon, the downdraft. These are not gentle currents but massive, convective cells of sinking air, where parcels of the cooler, denser atmosphere from the upper layers plunge toward the scorching surface. Caught in one of these invisible rivers of descending air, a habitat could be pulled down into progressively hotter, denser, and more acidic layers. The windows, designed for the mild conditions of the 50th kilometer, would begin to crack under the increasing pressure. The external cladding, though acid-resistant, has a temperature limit, and at depths below 40 kilometers, the heat would start to compromise its integrity, leading to a catastrophic failure. Every second of descent would bring the colony closer to an environment where survival is impossible. To counter this, the habitats would be equipped with multiple, redundant emergency systems. The most critical would be large banks of ultracapacitors or flywheel energy storage, designed to provide a massive, short-term burst of power to the thrusters specifically for dodging these downdrafts. If main power failed, these systems would kick in automatically, firing the thrusters at full capacity to push the colony laterally out of the sinking air column and into a more stable layer, fighting gravity with a desperate surge of energy. As a last resort, habitats might even carry emergency balloon systems separate, pressurized volumes that could be rapidly inflated with helium or hydrogen extracted from stored water, providing a quick burst of additional lift to arrest a descent, a final parachute made of air. Acknowledging these hidden risks doesn't diminish the achievement. It highlights the incredible courage and foresight it would require. The pioneers choosing to live in the clouds of Venus would be placing their trust not in invincible technology, but in resilient, redundant, and brilliantly conceived safety systems. They would be accepting a life where vigilance is constant and emergency drills are a regular part of the routine, all for the chance to be part of humanity's most audacious step into the cosmos. It's a testament to the human spirit that we can look at such a daunting list of dangers and still see not a forbidding warning, but a challenge to be met and overcome. And so we arrive at the grandest, most audacious question of all. What if these cloud cities are not the end goal, but merely the scaffolding for the most ambitious engineering project in human history? The floating habitats, for all their elegance, represent a life lived in a carefully managed bubble, forever separate from the world below. But the human spirit is not content with mere isolation. It dreams of transformation. It dreams of terraforming, of taking a hostile planet and reshaping it, molecule by molecule, into a verdant, living world. And for Venus, this dream begins not on the surface, but from the very clouds we propose to call our first home. The scale of this challenge is almost incomprehensible. Venus's problems are fundamental: a surface hot enough to melt lead, an atmosphere 90 times thicker than Earth's and composed almost entirely of carbon dioxide, and a crippling lack of water. To fix this, we wouldn't be gardening, we would be performing planetary-scale surgery. The first and most logical step would be to address the extreme greenhouse effect. One of the most discussed mega projects involves constructing a giant solar shade, positioned at the Lagrange point between Venus and the Sun. This vast, gossamer-thin structure, perhaps built from asteroids mined for their reflectivity, would cast a permanent shadow over the entire planet, blocking a significant percentage of solar radiation and allowing the surface to begin a slow, agonizingly gradual cool-down over centuries. It's a project that dwarfs anything we have ever conceived, a testament to patience and long-term thinking on a scale we are only beginning to grasp. While the planet cools, the work of overhauling the atmosphere could begin, and this is where our cloud cities become the essential command and control centers. The same atmospheric processes that create breathable air for the habitats could be scaled up to an industrial magnitude, acting as giant carbon scrubbers in the sky. But why stop with human-made machines? This is where science fiction offers a truly elegant biological solution, seeding the upper cloud decks with specially engineered microbes. Scientists have already discovered extremophile bacteria in Earth's upper atmosphere that metabolize trace gases. We could design synthetic organisms painstakingly crafted in the labs of the cloud cities to perform a specific planet-altering task, consuming carbon dioxide and sulfur dioxide and converting them into solid carbon, oxygen, and other stable, harmless compounds that would slowly rain down out of the atmosphere. These microscopic terraformers would work continuously for generations, slowly thinning the oppressive sky and revealing the stars above for the first time in billions of years. The final and most dramatic hurdle is water. A true Earth-like planet needs oceans, and Venus is bone dry. The most speculative solution involves redirecting comets or ice-rich moons from the outer solar system, perhaps from the rings of Saturn or the Kuiper belt, on a carefully calculated collision course with Venus. The sheer kinetic energy of these impacts would have to be meticulously managed to avoid catastrophic damage, with the objects fragmented to burn up in the atmosphere, delivering their precious water vapor as rain over millennia. It is a staggering concept, a celestial billiards game played with moons as the cue balls and an entire planet as the table. The cloud cities, positioned safely above the chaos, would monitor and guide this epic delivery of the building blocks of life. This vision transforms our floating outposts from isolated arcs into the nerve centers of a planet-wide rebirth. They are the beachhead, the permanent foothold from which we can direct this multi-thousand-year project. The scientists living there would become planetary gardeners on the grandest possible scale, patiently tweaking the biological and chemical systems they've put in motion, monitoring atmospheric thickness, surface temperature, and the gradual accumulation of water. They would witness the slow-motion miracle of a world being remade, a process so gradual that no single generation would see its completion, but each would contribute to a legacy that echoes across millennia. This long-term vision redefines the purpose of settling Venus. It's not about escaping a troubled Earth, but about exercising our highest capacity for stewardship and creation, applying our intelligence to nurture a second living world in our solar system, and forever securing the future of life itself. Of course, this is a vision of breathtaking ambition, but to present it fairly, we must also give voice to the scientists and thinkers who look at these plans with profound skepticism. Their criticisms are not born of a lack of imagination, but from a deep concern that we are underestimating a host of colossal challenges, both technical and human. The most pressing of these concerns begins with the very air the city would float in. Skeptics argue that while we have materials resistant to acids on Earth, we have never attempted to maintain a large-scale, permanent structure in a continuous bath of concentrated sulfuric acid mist under high wind loads. The comparison to industrial settings on Earth, they point out, falls short. A chemical plant has the advantage of solid ground, easy access for constant maintenance, and the ability to shut down entire sections for repair. A floating habitat has none of that luxury. The stress on every seal, every joint, every external sensor would be unrelenting. A single, unforeseen failure in a critical acid-resistant coating could lead to a cascade of structural compromises, and performing complex external repairs while buffeted by 300 km/h winds is a scenario for which we have no real-world precedent. It's not that it's impossible, they concede, but that the margin for error is vanishingly small, and the consequences of even a minor miscalculation are catastrophic. Beyond the physical corrosion of machines, these critics highlight a potentially even greater vulnerability: the human mind. They question whether we have fully considered the profound psychological impact of living in a world without land. For our entire evolutionary history, humanity has been grounded, quite literally. We have a deep, instinctual connection to terra firma. The proposal to live permanently suspended in a featureless, golden haze with no horizon, no changing seasons, and no ability to ever step outside and feel solid ground beneath our feet could be a recipe for a unique form of madness. The visual monotony alone could be deeply oppressive, leading to sensory deprivation and depression. Furthermore, the knowledge that your entire existence depends on the integrity of a bubble of air, that a mistake could send you plunging into a crushing, infernal abyss, could create a baseline level of existential anxiety that would be intolerable for many. While virtual reality might offer an escape, it could also deepen a sense of disconnection and unreality. Proponents talk of spacious atriums, but skeptics worry they would feel less like parks and more like very comfortable cages, unable to ever truly alleviate the deep-seated human yearning for a connection to a natural outdoor world. This leads to perhaps the most powerful ethical criticism leveled against the entire concept: the argument of misplaced priority. Detractors ask a very pointed question: why would we dedicate trillions of dollars and the efforts of our brightest minds to building a habitable environment in the clouds of Venus when we are failing so spectacularly to maintain the one we already have on Earth? They see it as the ultimate expression of escapist fantasy, a desire to abandon a planet we have damaged rather than commit to the difficult, unglamorous work of fixing it. The technologies developed for Venus closed-loop life support, advanced renewable energy, carbon sequestration are precisely what we need to solve our problems on Earth. Would that investment not be better spent deploying them here now for the benefit of billions rather than for a few thousand pioneers in the sky? This perspective frames Venus not as a noble next step, but as a distraction, a dangerous dream that siphons away resources, political will, and public attention from the urgent environmental crises unfolding on our own world. Finally, many in the scientific community remain staunchly convinced that Mars is simply a more logical and prudent choice for humanity's first off-world colony. The Martian challenges low gravity, radiation, thin atmosphere are severe, but they argue these are challenges we understand in a more straightforward, mechanical way. Building on a solid surface, mining local regolith for radiation shielding, and exploring a landscape with canyons and mountains feels more tangible and manageable than engineering a city to dance upon hurricane-force winds. Mars also offers clearer scientific returns in the search for past or present extraterrestrial life, a goal of paramount importance. From this viewpoint, Venus is a fascinating but secondary target, a complex puzzle to be solved after we have first secured a foothold on a world that, for all its hostility, at least provides the psychological and practical comfort of solid ground. Engaging with these criticisms isn't a weakness of the vision, it is its essential strengthening. It forces the conversation to be honest, grounded, and ultimately more robust, ensuring that if we do one day set sail for the Venusian skies, we will do so with our eyes wide open to every danger and every doubt. And perhaps the most exciting part of this entire vision is realizing that it isn't a distant story unfolding without you. It's a future that is actively being built right now, and it needs architects, builders, and dreamers. The skills required to design a city floating in the acidic clouds of Venus read like a blueprint for the next generation of scientific pioneers. It starts with aerospace engineering, but not as we know it today. This field will evolve to create a new discipline of atmospheric architecture, designing structures that are both habitat and vessel, mastering the principles of buoyancy and material science to build homes that can dance on hurricane-force winds. Every strut of a geodesic dome, every thruster for station keeping, and every calculation for stability in a super-rotating atmosphere will come from the minds of those who dare to reimagine what a building can be. The very air we breathe in that golden haze will be conjured by chemists and chemical engineers who see a toxic atmosphere not as a barrier but as a reservoir. They will design the processes to crack carbon dioxide into breathable oxygen and harvest trace nitrogen, turning the planet's greatest threat into its most vital resource. Their work will blur the lines between alchemy and industry, creating closed-loop systems where waste is an obsolete concept. Alongside them, biologists and botanists will become masters of closed ecological systems, engineering the aeroponic farms and bioreactors that will turn human waste back into food and oxygen, creating the self-sustaining biospheres that are the true lifeblood of any off-world colony. They won't just be growing plants, they will be engineering entire ecosystems in miniature, perfecting the balance of life in a bottle. But a city is more than its physical shell and life support, it's a society. This is where the social sciences become as critical as the hard sciences. Psychologists and sociologists will be essential to understanding how humans cope with sensory monotony, radical isolation, and the lack of natural day-night cycles. They will design the communal spaces, the virtual reality escapes, and the social structures that prevent a community from fracturing under the immense psychological pressure of their environment. Their insights will determine the difference between a thriving civilization and a failed experiment. And none of this happens without the roboticists and AI specialists who will create the autonomous workforce. The drones that perform external maintenance in corrosive conditions and the intelligent systems that manage the millions of data points required to keep the city safely afloat. They are the unsung guardians, the ones who build the safety net that allows humanity to dream so boldly. You don't have to wait for a degree to start contributing to this future. The path begins today. For students captivated by these ideas, pursuing STEM subjects in school is the first step on that journey. But engagement doesn't start or end in a classroom. Organizations like the Planetary Society are fantastic hubs for space advocates, offering a way to stay informed, support mission advocacy, and connect with a global community of enthusiasts and professionals. For a more hands-on approach, NASA citizen science programs invite everyone to contribute to real research. You could be classifying galaxies, identifying features on other planets, or even helping to train algorithms to recognize signs of life, all from your home computer. You are not just a passive observer of this story. You can be one of the many hands helping to write it, line by line, discovery by discovery. This incredible future of cities in the clouds isn't something that will simply happen to us. It is something we will build piece by piece through the collective curiosity, courage, and determination of countless individuals who looked at the sky and decided to reach for it. And so our journey through the golden haze of Venus comes to a close, not at an ending, but at a beginning. We've voyaged from a shimmering point in the night sky to a detailed blueprint for a new chapter in human civilization. We've seen how a world with a surface that can melt lead harbors, high in its atmosphere, a pocket of near-Earth normalcy, a place where the very air we breathe can become the foundation for our homes. We've explored the technologies from acid-resistant alloys and atmospheric processors to closed-loop agriculture and planetary-scale energy systems that could transform this vision from a captivating thought experiment into a tangible, if staggering, engineering project. This isn't just wild science fiction. It is a possibility grounded in the rigorous application of real science, a challenge that speaks directly to our innate human drive to explore, to adapt, and to push the boundaries of the possible. The obstacles are immense, from managing the corrosive clouds and navigating hurricane force winds to confronting the deep psychological and ethical questions of reshaping another world. Yet, each hurdle presents not a reason to stop, but a problem to be solved, an innovation waiting to be born. The very act of attempting this would force breakthroughs in sustainability, material science, and closed-loop living that would reverberate back to Earth, offering solutions to our own planetary challenges. To make a home in the clouds of Venus would be one of the most audacious and awe-inspiring endeavors we could ever undertake. It would redefine our place in the cosmos, proving that we are not limited to worlds that are ready for us, but can learn to make ourselves ready for any world. Success would mean more than just a new address for humanity. It would represent our evolution into a truly multi-planetary species, forever securing the future of life and thought against any single planetary catastrophe. It is a testament to curiosity, courage, and our boundless capacity for ingenuity. The future isn't just something that happens to us. It's something we build line by line of code, equation by equation, and dream by dream. The conversation about where we go next is happening now in laboratories, universities, and space agencies around the world. What part will you play? Will you be the engineer who designs the first acid-proof composite, the botanist who perfects sky-borne agriculture, or the visionary who advocates for the mission? Your curiosity is the first, most crucial fuel for this journey. If this vision of a city sailing the endless sunset of Venus sparked your imagination, then help us keep exploring the edges of what's possible. Give this video a like if you want to see more deep dives into humanity's next giant leaps. Subscribe to the channel so you don't miss our next adventure, and let us know in the comments, could you see yourself volunteering for a one-way ticket to a life among the clouds? What questions about our future in space are you burning to have answered next? The discussion starts with